Hey guys, so in this video we will be covering Algebra 2, Lesson 2, and it's the parent functions. And let's go. Okay, so before we dive into these functions, you need to know some definitions. So the first one is domain, which is the set of all the possible x values of a function. Range is the like domain, but now it's the set of all possible y values of a function. Then there's x-intercepts and y-intercepts. So that's really when the line or curve crosses the x or y-axis respectively. And the ordered pair there is called the x-intercept or y-intercept. And then there are lines that are called asymptotes. And that means these are lines that continually reach a point but never meet it. So, like, there's a function, right? That kind of goes like this. And see how this line, let me draw this arrow again. Okay, it's fine. Keeps going to 0, but it will never touch it because there's an asymptote there. So it's like a barrier. Now there's the inverse function. So it's the opposite or the reverse of the original function. I have a separate video planned about inverse functions, and we will dive into more about solving them and such. And then there's even or odd symmetry, and this means that whether or not the function has symmetry with respect across the y-axis, or even symmetry, or across the line y equals x, which is odd symmetry. And then a vertex is a corner or a point where lines meet. So, like, this is the quadratic function, right? And see this point here? This is where the two lines kind of meet together, or curves, I would say, and that's the vertex. So let's get to our first function. So this is the function f of x equals x, and the domain is from negative infinity to positive infinity, and range is again negative infinity to positive infinity. The inverse of this function is itself, so y equals x. There's not really a vertex, but you could say the equation of this function is y equals mx plus b, something you learn in like pre-algebra, so not going to go much into it. And then this function has odd symmetry, since if you reflect it across itself, you'll get itself, because the definition of odd symmetry means reflecting over the line y equals x. Now we have this function f of x equals the absolute value of x, and the domain is from negative infinity to positive infinity. In the range, I put it as 1, but technically it's anywhere from 0 to infinity, because f of the absolute value of x, right, it has to be positive. Even if you take the absolute value of like -7, you'll get 7, because that's just the property of the absolute value. So that's why it looks like a v. There is no inverse of this function, but and vertex technically is at the origin, but you can express it as f of x equals a times the absolute value of bx minus h times plus k, where the vertex is at the point h comma k. That's where the vertex is. And then this is an even function since it has symmetry reflected over the y-axis, as you can see on the graph. And let's move on. Now we have the function f of x equals x squared, or some may express it as ax squared plus bx plus c. Either way works. And the domain is from negative infinity to positive infinity, and the range is from, well, I put 1, but from 0 to infinity. And this is the parent function, so we will keep the domain mesh like that, but this function can be manipulated to have different domains and ranges, depending on how you transform it. The inverse is y equals the square root of x, where x is larger than 0, because if you have a negative square root, you get imaginary numbers, and that's just a mixed bag that I will not go into right now. And the vertex here is at the origin, but generally it is expressed as f of x equals a times bx minus h squared plus k, where hk is the vertex, and this is why they call it vertex form. And this is an even function since it has symmetry with respect to the y-axis. Now we have the function, the f(x) equals the square root of x, and the domain here is from really 0 to infinity, and the range is also from 0 to infinity. And then the inverse is y equals x squared if x is larger than 0 or equal to. And the vertex is f of x equals a times the square root of bx minus h plus k, where h comma k is the vertex. And then there is no symmetry for this function. Now we have the function x cubed, and the domain is like linear function where it is negative infinity to positive infinity, and the range is negative infinity to positive infinity. And the inverse is the cube root of x, and the vertex for this parent function is at the origin, but generally it is a times bx minus h cubed plus k, where h comma k is the vertex, and it has odd symmetry since it is reflected over the line y equals x, like symmetry with respect. My bad. Now we have the function f of x equals the cube root of x, and unlike the square root of x, this has domain from negative infinity to positive infinity and range from negative infinity to positive infinity, even though, albeit, it goes quite slow going up to larger ranges, but we're talking about infinity here. So the inverse is y equals x cubed as long as x is larger than 0 or equal to. The vertex here is 0 comma 0 for the parent function, but generally it is a times the cube root of bx minus h plus k, where hk is the vertex, and this has odd symmetry. Now we're looking at the first function where there is an asymptote, and it's f of x equals b to the power of x, or they call it the exponential growth function if b is larger than 1. So the domain is from negative infinity to positive infinity, and the range is from 0 to infinity, because there's an asymptote at the line y equals 0. As you can see, the function is approaching 0, but never really gets to it. And the vertex here for the parent function is 0 comma 1. But the vertex can be generally expressed as a times b to the power of x minus h plus k, where hk is the vertex, and there is no symmetry for this function. Now for this function, it has all the same properties of the other function that we just saw on the previous slide, but now it is exponential decay because x is from 0 to 1, so it's not larger than 1. And one more thing to say is that the inverse of this function is what they call log base b of x. Log base b of x. And now it's not too important for you guys to know what this function is yet, because we will go into more depth later on about logarithms. But for now, just know that the inverse of an exponential function is log times log base b of x. And yes, there are other functions we will learn in Algebra 2, including log of x, natural log of x, and rational functions like 1 over x or 1 over x squared, and graphs of other various polynomials. But for now, as long as you understand all the other previous functions and can mentally picture their parent functions in your head, you should be good. And thanks for watching this video. Comment if you have any questions, and see you guys in the next one.